In mathematics, a power series is an infinite series of the form where n represents the coefficient of the nth term, c is a constant, and x varies around c. This series usually arises as the Taylor series of some known function. In many situations c is equal to 0, for instance when considering a Maclaurin series. In such cases, the power series takes the simpler form. These power series arise primarily in analysis, but also occur in combinatorics and in electrical engineering. The familiar decimal notation for real numbers can also be viewed as an example of a power series, with integer coefficients, but with the argument texts fixed at 1/10. In number theory, the concept of p-adic numbers is also closely related to that of a power series. Examples: any polynomial can be easily expressed as a power series around any center C, although most of the coefficients will be 0 since a power series has infinitely many terms by definition. For instance, the polynomial can be written as a power series around the center as, or around the center as, or indeed around any other center C. One can view power series as being like polynomials of infinite degree, although power series are not polynomials. The geometric series formula, which is valid for, is one of the most important examples of a power series, as are the exponential function formula and the sine formula valid for all real x. These power series are also examples of Taylor series. Negative powers are not permitted in a power series, for instance is not considered a power series. Similarly, fractional powers such as are not permitted. The coefficients are not allowed to depend on, thus for instance, is not a power series. Radius of convergence. A power series will converge for some values of the variable x and may diverge for others. All power series f in powers of will converge at x equals c equals a0 requires interpreting the expression OO is equal to 1. If c is not the only convergent point, then there is always a number r with 0 less than r infinity such that the series converges whenever x minus c less than r and diverges whenever x minus c greater than r. The number r is called the radius of convergence of the power series. In general it is given as or, equivalently. A fast way to compute it is if this limit exists. The series converges absolutely for x minus c less than r and converges uniformly on every compact subset of x minus c less than r. That is, the series is absolutely and compactly convergent on the interior of the disk of convergence. For x minus c equals r, we cannot make any general statement on whether the series converges or diverges. However, for the case of real variables, Abel's theorem states that the sum of the series is continuous at x if the series converges at x. In the case of complex variables, we can only claim continuity along the line segments starting at c and ending at x. Operations on power series. Addition and subtraction. When two functions f and g are decomposed into power series around the same center C, the power series of the sum or difference of the functions can be obtained by term-wise addition and subtraction. That is, if, then multiplication and division with the same definitions above. For the power series of the product and quotient of the functions can be obtained as follows. The sequence is known as the convolution of the sequences, and for division, observe, and then use the above comparing coefficients. Differentiation and integration. Once a function is given as a power series, it is differentiable on the interior of the domain of convergence. It can be differentiated and integrated quite easily, by treating every term separately. Both of these series have the same radius of convergence as the original one. Analytic functions. A function f defined on some open subset U of R or C is called analytic if it is locally given by a convergent power series. Every power series with a positive radius of convergence is analytic on the interior of its region of convergence. All holomorphic functions are complex analytic. Sums and products of analytic functions are analytic, as are quotients as long as the denominator is non-zero. If a function is analytic, then it is infinitely often differentiable, but in the real case the converse is not generally true. For an analytic function, the coefficients n can be computed as where denotes the nth derivative of f at c, and this means that every analytic function is locally represented by its Taylor series. The global form of an analytic function is completely determined by its local behavior in the following sense. If f and g are two analytic functions defined on the same connected open set U, and if there exists an element Cu such that f equals g for all n0, then f equals g for all xu. If a power series with radius of convergence R is given, one can consider analytic continuations of the series, i.e., analytic functions f which are defined on larger sets than x minus c, less than R, and agree with the given power series on this set. The number R is maximal in the following sense. There always exists a complex number x with x minus c equals R such that no analytic continuation of the series can be defined at x. The power series expansion of the inverse function of an analytic function can be determined using the Lagrange inversion theorem. Formal power series. In abstract algebra, one attempts to capture the essence of power series without being restricted to the fields of real and complex numbers, and without the need to talk about convergence. This leads to the concept of formal power series, a concept of great utility in algebraic combinatorics. Power series in several variables. An extension of the theory is necessary for the purposes of multivariable calculus. A power series is here defined to be an infinite series of the form where J equals as a vector of natural numbers. The coefficients are usually real or complex numbers, and the center C equals an argument X equals are usually real or complex vectors. In the more convenient multi-index notation this can be written: the theory of such series is trickier than for single variable series, with more complicated regions of convergence. For instance, the power series is absolutely convergent in the set between two hyperbolas. On the other hand, in the interior of this region of convergence one may differentiate and integrate under the series sign, just as one may with ordinary power series. Order of a power series. Let alpha be a multi-index for a power series F. The order of the power series F is defined to be the least value, alpha, such that are alpha 0, or 0 if f 0. In particular, for a power series F in a single variable x, the order of F is the smallest power of x with a non-zero coefficient. This definition readily extends to Laurent series.